A vast cosmic city holds 25 secrets that defy our understanding of reality. We are talking about the Hercules Cluster, a sprawling metropolis of galaxies located over 500 million light-years from Earth. By the end of this journey, you will see the universe in a completely new way through its most profound and puzzling contradictions. What happens when a cluster's hot gas simply vanishes, and why are there ghostly galaxies here that should not exist? The answers we are finding challenge the very foundations of modern astrophysics. What does it mean when the cosmos itself seems to break its own rules? This cosmic contradiction begins with a single, staggering structure. At the heart of the Hercules Cluster lies a supergiant elliptical galaxy known as Hercules A. It is a titan, and from its core erupts one of the largest structures in the observable universe, twin jets of superheated plasma, each stretching over 1 million light-years into the void. To put that in perspective, if you could see these jets with your naked eye, they would span an area of the sky 20 times wider than the full moon. They are colossal rivers of energy powered by the galaxy's central supermassive black hole. Yet, for all their predictable scale, these jets behave in a deeply unpredictable way. Astronomers monitoring them have recorded a strange, rhythmic pulse. The jets don't shine with a steady light. Instead, they brighten and dim in a periodic pattern that defies every known model of black hole activity. It is as if a lighthouse with a beam 1 million light-years long is flickering on and off to a beat we cannot hear. Even more puzzling are the bright, concentrated knots of radio emission studded along the jet's length. These are not smooth streams, but turbulent, glowing islands of intense energy. What could possibly cause such a vast and powerful structure to flicker and knot in this way? The leading theories sound like science fiction. One idea suggests the black hole itself is wobbling or precessing, like a spinning top slowly tilting on a table. This wobble would cause the jets to sweep across space, lighting up different clouds of gas as they go. Another, even more exotic proposal points to the invisible scaffolding of the cosmos, dark matter. Could vast, diffuse clouds of this mysterious substance be drifting through the jets, interacting with the plasma and causing these brilliant, temporary hotspots? Hercules A's anomalous jets are our first direct clue that the rules governing even the most well-understood cosmic engines might be incomplete here. The cluster itself seems to be whispering that normal physics on this grander stage might just be a local ordinance. These flickering jets are not the only thing missing from the cosmic ledger. To truly map the Hercules Cluster, astronomers turn their most powerful X-ray telescopes toward it, expecting to see the telltale glow of a superheated atmosphere. In a normal galaxy cluster, the immense gravity holds captive a vast sea of gas known as the intracluster medium. This gas is heated to millions of degrees, making it shine brightly in X-ray light, and it typically contains more mass than all the cluster's stars combined. It is the cluster's lifeblood, its defining feature. But when scientists looked at Hercules, they found ghost towns. Large, sprawling regions within the cluster showed a shocking lack of this brilliant X-ray emission. It was like looking at a map of a major city and finding entire districts with no electricity, no heat, no signs of life. The intracluster medium, the very thing that should be binding this cosmic metropolis together, was simply not there. Where did it go? One leading theory is as dramatic as it sounds: a colossal, ancient collision. Picture two of the universe's largest structures, each containing hundreds of galaxies, slamming into each other at unthinkable speeds. Such a merger could have acted like a cosmic wrecking ball, violently stripping away the hot gas and flinging it out into the intergalactic void. The shockwaves from that impact could have disrupted the gas so thoroughly that it never settled back into a smooth, glowing halo. The ghost regions we see today would be the scars of that primordial catastrophe, but there is a competing and perhaps even stranger idea. What if the gas never left? What if it is still right there, but in a form we cannot see? Some models suggest an unknown physical process caused the intracluster medium to cool down with impossible efficiency. Instead of staying at millions of degrees and glowing in X-rays, it collapsed into a cold, dark state, perhaps forming vast reservoirs of faint stars or even coalescing into invisible clouds of molecular gas. This would be a radical departure from how we understand these environments to work. The missing atmosphere of the Hercules cluster presents a fundamental choice. Are we looking at the aftermath of a violent historical event, or are we witnessing a quiet, ongoing process that defies our textbooks? The answer changes how we view every giant cluster in the cosmos. This absence of hot gas creates a strangely pristine environment, one that may have allowed for the preservation of cosmic ghosts. Deep within a sub-region of the cluster known as Abell 2151, astronomers have discovered a haunting population. They are called ultra-diffuse galaxies, and they are some of the most enigmatic objects in the modern universe. Picture a galaxy the size of our own Milky Way, a vast, sprawling disk spanning 100,000 light-years. Now, imagine that this immense structure contains only 1% of the stars you would expect. That is an ultra-diffuse galaxy. They are colossal, fluffy ghosts, enormous in size but almost transparent, with their stars spread so thin that you could look right through them. In most places, these objects are rare curiosities, but here, in this pocket of the Hercules cluster, they are everywhere. There are far more of these failed galaxies than any theoretical model predicted. Their overpopulation is a direct challenge to our story of how galaxies are born and how they die. According to standard theory, a place like the Hercules cluster should be a galactic graveyard. Its immense gravity and turbulent history should have torn apart fragile, fluffy objects like ultra-diffuse galaxies long ago. They should have been shredded into streams of stars or swallowed whole by larger neighbors. Yet they persist. So what are they, and why are there so many? One compelling idea is that they are primordial relics. These ghostly galaxies might be fossils from the early universe, objects that formed in a quieter time and somehow survived the cluster's violent merger history untouched. Their dark matter halos, the invisible gravitational scaffolding that holds every galaxy together, might be unusually dense and spread out, protecting their few stars from being stripped away. This would mean they are not failed galaxies but triumphant survivors. The opposing theory is far more violent. Perhaps they are not survivors but casualties. These ultra-diffuse galaxies could be the shredded remains of once normal galaxies that ventured too close to the cluster's heart. The immense tidal forces, like cosmic gravity stretching and pulling, could have ripped away most of a galaxy's stars and gas, leaving behind only its bloated, diffuse core. In this scenario, their abundance is a sign of the cluster's destructive power, not its preservation. The mystery cuts to the core of dark matter itself. If these objects are primordial, their unusual structure tells us that dark matter can clump in ways we never anticipated. If they are shredded remains, then our models of how gravity shapes galaxies within clusters are missing a key piece. The silent, fluffy ghosts of Abell 2151 are not just oddities. They are evidence that the most common form of matter in the universe, the dark matter that shapes everything, might behave in unexpected ways in the extreme environment of a cluster. Their very existence asks a profound question. In the cosmic metropolis, are the quietest inhabitants the oldest residents, or are they the ones who have suffered the most? The silent, fluffy ghosts of Abell 2151 point to a deeper cosmic architecture, one that stretches far beyond the cluster's own borders. Our view now must expand because the Hercules cluster itself appears to be a single, luminous knot in a web of unimaginable scale. It is connected to one of the most staggering structures humanity has ever identified, the Hercules corona Borealis Great Wall. This is not a wall of bricks or stone, but a filament, a vast, thread-like superstructure composed of galaxy clusters and superclusters, all bound together by gravity. Its dimensions are almost incomprehensible. The Great Wall stretches for roughly 10 billion light-years across the observable universe. To grasp that scale, consider this: light, the fastest thing in existence, would need 10 billion years to travel from one end to the other. This single structure spans nearly a tenth of the entire visible cosmos, and nestled within its immense scaffolding, like a city built along a continental mountain range, is our Hercules Cluster. This proximity creates a profound and unsettling mystery. According to a foundational principle of cosmology known as the cosmological principle, the universe on the largest scales should look roughly the same everywhere. Matter should be distributed with a kind of statistical smoothness. There should not be gigantic, glaringly obvious structures that stand out and dominate vast volumes of space, especially not in the early universe. The Hercules Corona Borealis Great Wall, by its sheer size and its apparent connection to Hercules, seems to violate this principle. It is a cosmic anomaly of the highest order. The central question is not just what it is, but how it could possibly exist. How could gravity have had enough time in the relatively young universe to pull together enough matter to form a structure 10 billion light-years long? Our best models of cosmic evolution struggle to explain it. It is as if we found a single 1,000-mile-long mountain range on Earth that formed in just a few years. The processes we understand simply do not work that fast. This makes the Hercules Cluster more than just a local mystery. It becomes a critical observation post, a keyhole through which we are peering at the universe's largest and most ancient skeleton. By studying the dynamics of Hercules, the motion of its galaxies, and the distribution of its dark matter, astronomers are essentially taking the temperature of the Great Wall itself. They are asking, does the gravitational influence of this colossal filament explain the strange, high-speed galaxy motions we see within Hercules? Could the violent merger history we suspect for the cluster be a direct result of its position within this vast cosmic watershed, where flows of matter on the largest scales are funneling galaxies together? The link suggests that the unexplained phenomena within the cluster, the missing gas, the ghost galaxies, the flickering jets, might not be isolated incidents. They could be local symptoms of a global condition, side effects of the cluster's embedded location within a structure so vast it challenges our understanding of the universe's infancy. The Hercules Cluster, therefore, is not merely an object of study. It is a messenger telling us that the cosmos on the grandest scale may be far more textured, far more structured, and far more mysterious than our smoothest theories allow. This invisible architecture leaves a visible signature, a ghostly fingerprint pressed into the very fabric of light. The immense collective gravity of the Hercules Cluster acts as a natural telescope, warping the space around it. Light from galaxies billions of light-years behind the cluster does not travel in a straight line to us. Instead, it bends around this colossal mass, creating spectacular optical illusions known as gravitational lenses. We see stretched, magnified, and often duplicated images of those distant background galaxies, transformed into brilliant arcs and perfect circles called Einstein rings. It is a beautiful confirmation of Einstein's theory of general relativity, but here in Hercules, the lens is telling a story that does not quite add up. The distortion is simply too strong. When astronomers measure the severity of these lensed arcs, like those famously surrounding the giant elliptical galaxy NGC 6047, they can calculate how much mass must be present in the cluster's core to cause such extreme bending. The answer they get is staggering, and it vastly exceeds the mass of everything we can see, all the stars, all the hot gas, all the dust. There is a profound deficit. This is the classic missing mass problem, but in Hercules, it is not just a number on a spreadsheet. It is etched into the sky as luminous, warped mirages. To understand why this is so puzzling, think of a magnifying glass. If you look through a simple, smooth lens, it distorts the background in a predictable, even way. But if that lens were full of invisible, dense lumps, the distortion would become patchy and irregular. The lensing in Hercules suggests something similar. The dark matter halo, the invisible gravitational scaffold that holds the cluster together, appears to be far more complex and clumpy than our best models predict. Our current maps, which assume a smooth, gradual distribution of dark matter, cannot generate the intense, localized lensing effects we observe around galaxies like NGC 6047. The arcs are too bright, too sharply curved. This means the dark matter is not a uniform fog. It is likely concentrated into dense, invisible knots and subhalos surrounding individual galaxies, or perhaps woven into massive, unseen filaments threading through the cluster's heart. Each anomalous arc is a direct measurement, a snapshot of gravity's fingerprint at a specific point, and those fingerprints reveal a hidden topography of mass that our telescopes cannot photograph. This clumpiness is a crucial clue. It suggests that dark matter, whatever it is, interacts with itself or with the cluster environment in ways we have not accounted for. Perhaps collisions and mergers between dark matter halos leave behind these dense cores. Or maybe dark matter is not a single, simple particle but a more complex substance with its own rich physics. The lensed arcs of Hercules are more than just cosmic curiosities. They are high-precision tools allowing us to trace the contours of the invisible. They show us that the true skeleton of the cosmos is not a smooth framework, but a tangled, intricate web of shadowy mass, and its most complex knots may be tied right here. These intricate maps of invisible mass reveal a hidden choreography, a strange and coordinated motion that should not exist. While studying the precise movements of galaxies within the Hercules cluster, astronomers began to notice a subtle but persistent pattern. It was not the random, chaotic dance expected in a mature cluster. Instead, a significant number of galaxies appeared to be streaming together, all moving along a preferred axis, as if pulled by some immense unseen hand. This coordinated drift has been given a haunting name, a dark flow. To understand why this is so bizarre, picture a beehive after a disturbance. The bees do not all fly in one unified direction. They erupt in a chaotic, buzzing cloud, each insect following its own frantic path. A mature galaxy cluster, having settled after its formative collisions, should resemble that cloud. The individual galaxies should have what scientists call random peculiar velocities, moving in all directions as they orbit the cluster's center of mass. The discovery of a preferred direction for so many galaxies is like seeing every bee in that hive suddenly turn and fly steadily toward the east. It suggests an external influence, a gravitational tug from something so vast its pull is felt across the entire half-million light-year expanse of the cluster. The debate over this dark flow is intense. Skeptics argue it could be an observational artifact, a trick of perspective or incomplete data. Perhaps we are not seeing a true coordinated motion, but instead witnessing the aftermath of a smaller, recent merger where a group of galaxies has not yet mixed into the general population. Yet the persistence of the signal in multiple studies makes this simple explanation feel increasingly strained. If it is real, the implications are staggering. The gravitational force required to orchestrate such a flow would have to come from an accumulation of mass beyond comprehension, a structure so enormous it lies far beyond the cluster itself, possibly even beyond the visible horizon of our universe. This leads to a truly mind-bending possibility. Could the Hercules dark flow be evidence of a gravitational pull from a cosmic structure so distant its light has not had time to reach us? Or even more radically, could it be an echo from a time before the Big Bang, a relic imprint from a prior state of the cosmos that set matter in motion on a universal scale? While these ideas venture into speculative realms, the observed alignment forces us to confront the limits of our cosmic vision. It hints that the Hercules Cluster, for all its immensity, may not be an isolated island, but a raft caught in a current flowing from depths of space and time we cannot yet see. This coordinated drift suggests the universe's greatest structures may be connected in ways that transcend our observable bubble, pulling on each other across voids of unfathomable scale. This coordinated drift through the cosmos leaves behind a silent, empty stretch of history. As astronomers meticulously charted the distances to thousands of galaxies in and around Hercules, they stumbled upon a profound silence. In a specific slice of space pointing away from the cluster, there is a puzzling gap in the cosmic record. It is known as the redshift desert. Redshift is the key tool for measuring cosmic distances. As the universe expands, light from receding galaxies is stretched, shifting its color toward the red end of the spectrum. The greater the redshift, the farther away and the further back in time we are looking. By conducting deep spectroscopic surveys which break starlight into rainbows to read these redshift fingerprints, scientists built a three-dimensional map of the region. And on that map they found a void for a specific range of redshifts corresponding to a specific chapter in the universe's middle age. The number of galaxies drops dramatically. It is as if you were reading a history book and found an entire century where barely any pages had been written. The immediate question is whether this desert is real or merely an illusion. Could it be a selection effect where our telescopes simply missed faint galaxies at that distance? Modern instruments are extraordinarily sensitive, making this explanation less likely with each new survey. Another possibility is cosmic shadowing. Perhaps an immense cloud of cold foreground dust is obscuring our view of that particular epoch, hiding galaxies from sight rather than implying their absence. Yet if the void is genuine, its implications are staggering. A true underdensity on this scale would mean that during a specific period, in a specific direction, the universe simply failed to make galaxies. What could cause such a universal pause? One provocative theory points to a phenomenon known as cosmic reionization. In the universe's infancy, the first stars and galaxies flickered on, their intense radiation burning away the fog of neutral hydrogen that filled space. This process was not perfectly uniform. It is possible that Hercules sits along a line of sight that pierced an unusually large and persistent bubble of this early ionized gas. Within such a bubble, the conditions for later galaxy formation might have been suppressed, leaving behind a fossilized imprint of that ancient transition, a barren stretch of time preserved in the cluster's backdrop. This desert forces us to confront the unevenness of cosmic history. If confirmed, it suggests that the story of galaxy formation is not a smooth, continuous narrative played out identically everywhere. Instead, it is a patchwork tale with some regions flourishing and others stalling, their timelines shaped by events from the universe's very first chapters. The Hercules Cluster, then, becomes more than a collection of mysteries. It is a unique vantage point. By studying this specific redshift desert, we are not just looking at an empty space. We are potentially looking back at the ghost of an event that shaped the entire large-scale structure of the cosmos. An event whose final echo is a strange, silent gap in the galactic chorus surrounding one of the universe's greatest cities. This silent desert in time points toward a core where the universe's energy budget simply does not balance. At the very heart of the Hercules Cluster, in the dense core surrounding its central galaxies, a fundamental law of astrophysics appears to be broken. It is known as the cooling flow problem. The physics behind it seems beautifully straightforward. We have a vast reservoir of superhot gas, the intracluster medium, trapped by immense gravity. This gas, at millions of degrees, should naturally lose energy by radiating X-rays out into space. As it loses that energy, it should cool down. Colder, denser gas should then sink under gravity toward the cluster's center, flowing inward in a steady river of material. And at the end of that river where this cooled gas pools, there should be a spectacular consequence, a frenzy of new star formation. It is a cosmic waterfall with a glittering pool of newborn stars at its base. This predicted cascade is called a cooling flow, and the observational evidence for it in Hercules is both clear and deeply confusing. X-ray telescopes see the telltale signature. The gas in the cluster's core is indeed cooling. We can see the radiation that proves it is losing energy. We can even detect the cooler, denser gas clouds that have condensed out of the hot atmosphere like mist forming over a warm ocean. The flow is happening, but when astronomers turn their optical telescopes to look for the expected stellar fireworks, they find only darkness. The burst of star formation, which should be visible as a brilliant blue glow of massive young stars, is almost entirely absent. The pool at the bottom of the waterfall is nearly empty. It is as if you watched a river pour into a vast basin, but the basin never fills. The water and the potential it represents simply vanishes. This leaves astrophysicists with a critical question. Where did all that cooled gas go, and why didn't it turn into stars? The leading answer points to a cosmic regulator, a balancing force of unbelievable power. The culprit is almost certainly the supermassive black hole at the cluster's very center. The theory, called active galactic nucleus feedback, proposes a dynamic battle. As gas cools and begins its inward flow, some of it inevitably feeds the central black hole. This does not happen quietly. As matter spirals into the black hole's accretion disk, it releases titanic amounts of energy, not as starlight, but as intense radiation and powerful jets of plasma, like those we see in Hercules A. This outburst acts like a cosmic furnace, blasting heat and turbulence back into the surrounding gas. It reheats the cooling atmosphere, shutting off the flow and preventing the runaway formation of stars. It is a self-regulating thermostat. Too much cooling triggers heating, which stops the cooling. The problem in Hercules is that the details of this thermostat are maddeningly vague. We see the cooled gas, we see the powerful jets from the black hole, but the connection between them, the exact mechanism by which the jet's energy couples to the gas and reheats it so efficiently without blowing it all away, remains one of the great unsolved puzzles in cluster physics. Does the energy transfer through sound waves rippling through the hot atmosphere, through bubbles of hot plasma inflated by the jets, or through some more subtle, poorly understood form of turbulence? The cooling flow problem transforms the cluster's heart from a predictable engine into a dynamic, feedback-driven system. It suggests that the most massive black holes in the universe are not just destructive monsters. They are essential governors controlling the growth of the galaxies that host them, and by extension, the entire cluster's evolution. The silent core of Hercules is not a failure of physics, but a testament to a hidden, ongoing negotiation between gravity and fury, where the potential for creation is constantly being recycled back into raw energy. This silent, regulated core exists within a structure that is anything but symmetrical. The Hercules cluster is not a smooth, spherical island in space. It is a cosmic wreck, a tangled mess of celestial debris. Its very shape tells a violent story. When you look at a deep image of the cluster, you don't see a neat, concentrated ball of light. Instead, you see a sprawling, lopsided, and elongated swarm of galaxies, as if a giant had taken two handfuls of stars and smashed them together. This irregularity is the first clue to its true nature. Hercules is not a single, peaceful entity. It is the product of a cataclysm, the ongoing aftermath of a head-on collision between two, or possibly even three, smaller galaxy clusters that began billions of years ago and continues to this very day. The evidence for this is etched into the motions of its inhabitants. By measuring the subtle redshift and blueshift of light from thousands of individual galaxies, astronomers can create a three-dimensional velocity map. It's like listening to a cosmic traffic report. In a calm, settled cluster, you'd expect to hear a balanced hum of galaxies orbiting in all directions. But in Hercules, the map reveals chaos. Galaxies are streaming in great rivers of motion, moving not in random orbits but in coherent, opposing flows. You can trace distinct groups of galaxies that are still rushing away from the point of impact, like splatter from a collision that happened in slow motion over cosmic eons. This is the ghost in the machine, the frozen echo of the initial trajectories from that primordial crash. The hot gas that permeates the cluster bears even more dramatic scars. X-ray observations show this atmosphere is not a placid, glowing halo. It is violently disturbed, stretched, and twisted into complex shapes. In some areas, the gas appears shock, heated to even higher temperatures, marked by sharp, bright edges that look like cosmic sonic booms frozen in space. In other regions, the gas has been completely stripped away, leaving those ghostly voids we discussed earlier. This disturbed gas is the equivalent of finding the twisted metal and skid marks at a crash site. It allows scientists to forensically reconstruct the angles and the sheer force of the impact. And herein lies the profound challenge: reconstructing a car crash where the vehicles are millions of light years across and the collision is still happening. The merger's ghost is faint, its signals mixed and blurred by billions of years of subsequent gravitational interactions. Pinpointing the exact trajectories, the precise speeds, and the original masses of the colliding clusters is a detective story of epic proportions. Did they hit straight on or at a glancing angle? Were they equal in size, or was it a case of a smaller cluster being consumed by a larger one? Each possible scenario leaves a different fingerprint in the galaxy motions and gas morphology we see today. Hercules, in all its messy glory, has become the universe's premier laboratory for studying cluster evolution through violence. By decoding this ghostly trajectory, we aren't just learning about one cluster's past. We are watching the fundamental process by which all the great structures in our universe grow, not through gentle accumulation, but through titanic, universe-shaking collisions. This violent, ongoing merger may have forged more than just ghostly trajectories. It might also have flung a cosmic monster into an unexpected hiding place. Deep within the Hercules cluster, tucked away in a small, unassuming dwarf galaxy, a brilliant beacon is screaming in X-ray light. Astronomers call it an ultra-luminous X-ray source, or ULX. By name alone, it sounds impressive, but its true nature defies simple explanation. This is not the gentle glow of a million stars. It is a single, point-like object, a cosmic lighthouse so intense that its X-ray output outshines our entire sun by a factor of millions. The sheer power of this thing creates an immediate problem. A typical stellar mass black hole, formed from the collapse of a single massive star, has a strict theoretical limit to how brightly it can shine, known as the Eddington limit. It's a balance between the inward pull of gravity and the outward push of radiation. Push too much energy out, and you blow your own fuel supply away. This ULX in Hercules is blasting far, far beyond that limit. It's a cosmic engine running in overdrive, and we need to figure out what's under the hood. Two leading candidates emerge from the theoretical garage, each more fascinating than the last. The first is an intermediate mass black hole. Think of this as the universe's missing link. We have plenty of evidence for stellar mass black holes, weighing a few dozen suns, and we know supermassive ones, millions to billions of solar masses, lurk in galactic centers. But the middle ground, black holes weighing a few hundred to a few 100,000 suns, has been elusive. A black hole of this size could naturally produce the staggering luminosity we see without breaking the known laws of physics. It would be a rare and precious discovery, a relic from the universe's early days when the first monstrous stars collapsed. The second candidate is a familiar object in an unfamiliar state, a regular stellar black hole on a cosmic binge. In this scenario, the black hole isn't unusually large, but it is feeding at a ferocious super Eddington rate. Imagine trying to drink from a fire hose. Most of the water would spray everywhere. Theorists suggest that if gas is funneling onto a black hole in a thick, dense disk, the radiation can be trapped and redirected, beaming out in powerful jets or cones. If that beam is pointed directly at us, it would appear artificially bright, like a lighthouse whose blinding beam sweeps across our ship. This would mean we're not seeing a new class of object, but a familiar one caught in an extreme and revealing pose. But the real mystery isn't just what it is, it's where it is. This ULX isn't in a giant elliptical galaxy at the cluster's heart. It's in a dwarf galaxy, a small, faint collection of stars. Dwarf galaxies are cosmic backwaters, not known for hosting such energetic powerhouses. Their gravitational wells are shallow, making it hard to hold onto the vast amounts of gas needed to fuel such an object. So how did it get there, and what is feeding it? The cluster's violent merger history might hold the key. The chaotic gravitational tides could have funneled gas into this otherwise quiet dwarf, triggering a sudden, spectacular feast. Or perhaps the object itself is an intruder, a black hole kicked out from the core of a larger galaxy during the collision, now wandering the cluster and finding temporary refuge in this small system. Finding a ULX here forces us to reconsider the life cycle of the most energetic objects in the universe. It suggests that the seeds of cosmic power can be planted in the most humble of gardens, and that a cluster's chaotic past can light unexpected fires in its quietest corners. That brilliant X-ray beacon is a single point of focused fury, but the cluster's true violence is painted across a canvas of staggering scale. Spanning millions of light-years, an immense and ghostly veil of radio light envelops the Hercules cluster. This is the Hercules radio halo, a so-called radio relic, and it is the fading echo of the most energetic event in the cluster's history. To understand what we're seeing, you have to think of the universe's most powerful particle accelerator. It isn't buried underground in a lab, it's the shock wave from a collision between galaxy clusters. When these titans merge, they don't just quietly bump together. They generate vast, supersonic waves of energy that race through the thin intracluster gas at thousands of kilometers per second. These merger shock waves act like cosmic pistons, compressing and energizing the sparse sea of particles and magnetic fields trapped between the galaxies. In the chaos, electrons are whipped to nearly the speed of light, becoming what physicists call relativistic. And when these ultra-fast electrons spiral along magnetic field lines, they release energy as synchrotron radiation, a specific type of radio wave we can detect with our telescopes. The Hercules radio halo is the faint, diffuse glow from this ancient continent-sized explosion. It is the cosmic afterglow of a catastrophe that happened billions of years ago. Maps of this halo reveal its breathtaking size, stretching over several megaparsecs, a structure so vast it could contain thousands of Milky Way galaxies laid end to end. Yet for all its grandeur, this relic presents a detailed puzzle. Its exact shape and the spectrum of its radio emission, how its brightness changes across different radio frequencies, don't perfectly match what our most sophisticated supercomputer simulations predict. According to the models, the shock waves from a major merger should leave behind a more structured, sharper-edged radio signature. The Hercules halo is fuzzier, more amorphous, and its radio light fades with frequency in a slightly unexpected way. This discrepancy has sparked a lively debate among astronomers. Are we looking at a single, simple shock wave or something far more complex? One leading idea is that we are seeing not one, but multiple shock waves superimposed on each other, like the overlapping ripples from several stones thrown into a pond at different times. This would make sense if the Hercules cluster is the product of a messy, multi-cluster collision, where shock fronts have crisscrossed and interacted over billions of years, creating a blended and confused radio echo. The competing theory is even more intriguing. It suggests the relic's unusual properties point to an ongoing, hidden source of energy. The relativistic electrons that produce the radio waves should lose their energy and fade away relatively quickly on cosmic timescales. The fact that we still see this vast halo implies that something must be reaccelerating those electrons, giving them a fresh boost long after the initial merger shock has passed. Could turbulence in the cluster's gas, stirred up by the continuing merger, be acting as a continuous cosmic accelerator? Or is there another, entirely unknown mechanism at work, one that keeps this ghostly radio shroud alive against all expectations? The Hercules radio halo is more than a beautiful artifact. It is a forensic snapshot of a billion-year-old explosion, and the details in that snapshot are telling us our story of cosmic collisions is still missing a few crucial pages. That fading radio echo points to a past of unimaginable violence, violence that may have fed a monster. At the absolute gravitational heart of the Hercules cluster sits a true leviathan, the galaxy NGC 6166. This is a CD galaxy, a cannibalistic supergiant that has grown fat by consuming its neighbors during the cluster's violent mergers, and at its silent core lies a supermassive black hole of almost incomprehensible scale. Recent measurements place its mass at a staggering 10 billion times that of our Sun. To put that number in perspective, the supermassive black hole at the center of our own Milky Way, Sagittarius A star, is a mere 4 million solar masses. The one in NGC 6166 is 2,500 times heavier. But the real mystery isn't its sheer size, it's that this black hole is too big for its home. Astronomers have discovered a surprising cosmic rule. The mass of a galaxy's central black hole is usually proportional to the mass of the galaxy's central bulge of stars. It's a tight correlation, suggesting that black holes and their host galaxies grow together, regulating each other's growth. NGC 6166 shatters this rule. Its black hole is significantly, puzzlingly overmassive. Compared to other galaxies with similar stellar bulges, its black hole is about 10 times heavier than it should be. It's like finding a tiny apartment with a furnace the size of a warehouse crammed into the basement. The scale is all wrong. How did this happen? One compelling theory is a story of cosmic gluttony, directly tied to the cluster's chaotic history. During the epoch of violent mergers that built the Hercules cluster, unimaginable amounts of gas would have been funneled toward the center. NGC 6166, as the dominant galaxy at the cluster's core, would have been the ultimate beneficiary of this galactic feast. Its black hole may have gorged itself on this torrent of material with freakish efficiency, growing at a rate that far outstripped the growth of the stars in the galaxy around it. It's a case of the engine growing faster than the vehicle it powers. The competing explanation is far more profound. What if the scaling relation itself is wrong, or at least incomplete, in the extreme environment of a galaxy cluster? Perhaps in these dense, violent metropolises, black holes can grow through channels we don't see in isolated galaxies. Maybe they can merge with other giant black holes flung from cannibalized galaxies, or feast on stars ripped from passing neighbors in ways that bypass the normal co-evolutionary process. This overmassive black hole isn't just a curiosity, it's a direct challenge. It forces us to ask whether our models of black hole and galaxy growth, built from studying quieter galactic neighborhoods, break down in the universe's most crowded and tumultuous cities. Is Hercules showing us an exception to the rule, or is it revealing a deeper, more complex rule we have yet to fully understand? That overmassive black hole at the cluster's core has flung its gravitational weight around for eons, but its influence seems to have limits. On the very fringes of the Hercules cluster, astronomers are tracking celestial renegades. These are galaxies caught in the act of a great escape, hurtling through space at velocities so immense they defy the cluster's mighty gravitational grip. We call them high-velocity galaxy ejecta, and their existence forces a fundamental question about the Hercules system: just how much energy is sloshing around inside it? To be flung out of a galaxy cluster is no small feat. You need an immense slingshot. The gravitational pull of a structure like Hercules is colossal. a deep well in the fabric of space-time from which escape requires a tremendous amount of kinetic energy. Think of it like launching a rocket from Earth. You need to achieve escape velocity to break free of our planet's gravity. For a galaxy to achieve cluster escape velocity, it must be given a phenomenal kick. The leading theory for where that kick comes from is written in the cluster's violent past. During the multi-cluster merger that built Hercules, the gravitational interactions were not just between the clusters as a whole, but between individual galaxies within them. In the chaotic three-body gravitational dances that ensued, it's possible for a smaller galaxy to get whipped around by two larger ones and flung out at incredible speed like a stone from a celestial catapult. This process, known as gravitational slingshotting, could explain these hypervelocity fugitives. They would be the shrapnel from the ancient collision, finally reaching the outskirts of the battlefield. But there is another, simpler possibility. What if these speedy galaxies are not escapees at all, but mere tourists? They could be interlopers, galaxies from the vast cosmic field that just happen to be passing through the cluster's neighborhood at a high speed, on trajectories that will eventually take them back out into the void. They are not bound to Hercules, they are just flying by. Distinguishing between a true ejector and an interloper is one of the great observational challenges here. It requires painstakingly precise measurements of a galaxy's radial velocity, how fast it's moving toward or away from us, and crucially, its proper motion, its sideways movement across the sky. Getting that full, three-dimensional velocity vector is incredibly difficult at such vast distances, yet for certain candidates the evidence is compelling. Studies have identified galaxies on the cluster's periphery with radial velocities so extreme that, even when accounting for the cluster's own motion, they appear to be well over 1,000 kilometers per second faster than the local escape velocity. They are, for all intents and purposes, unbound. The presence of these potential ejecta acts as a cosmic energy meter. The fact that Hercules seems capable of accelerating entire galaxies to such speeds tells us that the merger that formed it was not just massive, but exceptionally violent and dynamic. It deposited a staggering amount of kinetic energy into the system, energy that is still manifesting in these high-speed outliers. If they are true ejecta, they represent kinetic energy that has permanently left the cluster, a slight but measurable draining of its gravitational binding energy. This, in turn, helps astronomers map the depth and shape of the cluster's gravitational potential well, the very terrain of its space-time curvature, with greater precision. By asking why some galaxies are fleeing, we learn more about the forces that hold all the others together. These renegades on the edge are not just curiosities. They are forensic evidence of the cluster's most energetic historical moment, and a test of whether its gravity is strong enough to hold onto everything its violent birth created. Those renegade galaxies fleeing the cluster's grip speak to a history of profound disruption, a turbulence that has left its mark on the very center of power. In most of the universe's great galactic metropolises, the core is a place of eerie calm and immense density. This is the signature of a cool core cluster. Imagine the downtown of a massive, ancient city where the tallest skyscrapers are surrounded by orderly streets and a dense, settled population. In cosmic terms, the central galaxy sits in a deep, relaxed gravitational well, and the hot gas around it has had eons to settle into a smooth, dense, and, as the name implies, relatively cooler state. The temperatures here, while still in the millions of degrees, are distinctly lower than the gas in the cluster's outer regions. This dense, cool core is the hallmark of a mature, settled system that has not experienced a major collision in a very long time. It is the expected end state for a massive cluster like Hercules. Yet, when we look at Hercules' downtown, we find not order but chaos. The cluster is classified as a non-cool core or a disturbed cluster. The evidence for this is written in the X-ray light. Instead of a sharp, bright peak of dense gas at the center, the X-ray emission is messy, flattened, and spread out. The hot atmosphere shows no sign of having settled into a relaxed, concentrated pool around the central galaxy, NGC 6166. Furthermore, temperature maps reveal no distinct cool region in the heart. The gas in the core is just as hot, if not hotter in places due to shock heating, as the gas on the outskirts. This absence of a cool core is not a minor detail. It is a glaring clue about the cluster's recent life. A major merger between clusters is the most violent event in the universe since the Big Bang. Such a collision acts like a colossal blender, violently stirring the hot gas atmospheres of the colliding clusters. It disrupts the settled core, shocks and heats the gas, and flings it into a disturbed, turbulent state. The fact that Hercules still lacks a cool core tells us one critical thing. The merger that created it happened relatively recently on a cosmic timescale. The relaxation time for a cluster's core, the billions of years it takes for the stirred gas to radiate away its excess heat, settle back into the gravitational center, and form a new, dense, cool region, is immense. Hercules has not had enough time. This missing feature is a powerful chronometer. By analyzing just how disturbed the core gas is, astronomers can estimate how long ago the last major merger occurred. The evidence points to an impact that is still echoing through the system, an event that concluded perhaps only a couple of billion years ago. In the 13.8 billion year life of the universe, that is a recent trauma. So the lack of a cool core is far from a simple omission. It is a positive detection of youth and violence. Hercules is not an elderly, settled giant. It is a teenage cluster still roiling from the colossal growth spurt of its formative collision, its central streets still chaotic from the last cosmic parade that marched through. This disturbed heart confirms that the cluster we see today is a snapshot of an ongoing process, a dynamic entity caught in the long aftermath of its own violent birth. This turbulent youth has left its mark not just in disturbed gas, but in a faint, ghostly glow that fills the spaces between the galaxies. Drifting through the immense voids of the Hercules cluster, unattached to any single galaxy, are countless stars. They form a dim, pervasive haze known as intracluster light. To map this ethereal glow, astronomers must perform a kind of cosmic subtraction. Using the most sensitive optical telescopes, they take deep, painstaking images of the cluster. Then, with sophisticated software, they carefully mask out every identifiable galaxy, every bright star, every known source of light. What remains is a faint, complex tapestry of leftover light, the collective shine of these orphan stars. It is the ghost of the cluster's past, a fossil record written in starlight, and in Hercules, this ghost tells a particularly violent story. The intracluster light is not smooth and evenly distributed like a gentle fog. Instead, it is strikingly clumpy. It pools in great, faint streams and gathers in diffuse clouds, tracing out structures that span hundreds of thousands of light years. These are not random patterns, they are the gravitational scars of the cluster's formation. Each stream likely marks the path of a galaxy that was torn apart during the Great Merger. As galaxies passed close to one another, their mutual gravity acted like a cosmic tide, pulling long tails of stars out into the void. Other clumps are the ghostly remnants of entire dwarf galaxies that were completely dismembered, their stars now scattered into a faint, glowing cloud. The clumpiness is a direct map of the destruction. The more structured and pronounced the intracluster light, the more violent and recent the cluster's history of galactic cannibalism. Hercules, with its complex web of streams and clouds, confirms it endured a profoundly disruptive collision. But the plot thickens when astronomers analyze the color of this ghostly light. A star's color is a direct indicator of its age and composition. Young, massive stars burn hot and blue, while older, smaller stars glow with a cooler, redder light. By separating the intracluster glow into its constituent colors, scientists can take a census of these orphan stars. What they find is puzzling. the intracluster light in Hercules has an unusual color signature. In some regions, it appears unexpectedly red. This could mean the orphaned stars are, on average, older and more metal-rich than the stars still bound within the cluster's galaxies. How could that be? One possibility is that the merger preferentially stripped stars from the older, denser cores of galaxies, where stellar populations tend to be redder. It's as if the collision shook the oldest citizens from their homes first. Alternatively, the red color might hint that a significant portion of this light comes from the complete destruction of small, ancient dwarf galaxies, which are often dominated by old red stars. The competing observation is just as intriguing. In other areas, the intracluster light shows hints of a bluer tint. This suggests the presence of younger stars, which should not exist in the harsh environment between galaxies where there is no dense gas to form new ones. This blue mystery forces a radical rethink. Could some of these stars have formed in situ, right in the depths of intergalactic space? During the violent merger, colossal clouds of gas stripped from galaxies might have collided and compressed, triggering a late, desperate burst of star formation in the void itself. Or perhaps the blue light comes from a specific type of aging star that maintains a blue hue for longer than we thought. The color of this faint glow is more than an aesthetic detail. It is a clue to the origin story of the stars themselves. Are we looking at the scattered remains of the cluster's oldest inhabitants, or evidence of a final, frantic act of creation during its most violent chapter? The ghost light of Hercules holds the answer, a pale signature of chaos waiting to be decoded. The faint ghost light between galaxies is a record of ancient violence, but the cluster also broadcasts signals of a far more sudden and modern kind. Deep within the vast expanse of Hercules, a pinpoint of radio energy has been caught in the act of repetition. This is a fast radio burst, or FRB, but not the typical one-off event. This is a known repeater, and its location is a critical piece of the puzzle. Fast radio bursts are among the most enigmatic phenomena in modern astronomy. They are incredibly brief, lasting just milliseconds, but in that fleeting instant, they can release more energy than our sun puts out in 80 years. For a long time, they were cosmic ghosts, appearing once from random directions in the sky and then vanishing forever, leaving theorists with a blank slate for explanations. The discovery of repeaters changed everything. It proved that at least some of these bursts are not produced by cataclysmic, one-time events like a star exploding or two ultra-dense objects merging. Instead, they must come from a source that can survive the outburst and fire again. The repeater associated with Hercules is particularly special because astronomers have managed to localize it. Its precise coordinates trace back not to a giant elliptical galaxy at the cluster's heart, but to a smaller, star-forming galaxy within a small group that appears to be falling into the Hercules cluster for the very first time. This environmental context is a huge clue. Finding a repeating FRB in a galaxy that is entering a dense, violent cluster environment is like discovering a rare and fragile species of bird only in the turbulent updrafts at the edge of a hurricane. It suggests the extreme conditions of a cluster outskirts the immense pressures, the tangled magnetic fields. The shock waves from incoming gas might play a role in creating or triggering these bizarre events. The leading candidates for what causes FRBs are already exotic objects that thrive under pressure. One prime suspect is a highly magnetized neutron star called a magnetar. Picture the core of a giant star collapsed into a city-sized ball, with a magnetic field so powerful it could strip the information from every credit card on Earth from a distance of 100,000 miles. Theorists suggest that starquakes on the surface of such a magnetar, or sudden magnetic reconnection events in its atmosphere, could generate the colossal, focused bursts of radio waves we see. Another possibility involves an active galactic nucleus, where a supermassive black hole's chaotic environment could accelerate particles to produce coherent radio emission. The Hercules repeater's location adds fuel to this speculative fire. A galaxy group falling into a cluster is a place of immense dynamical stress. The gravitational tides can compress gas clouds, trigger bursts of star formation that lead to more magnetobirths, and stir up magnetic fields to unprecedented strength. Could the cluster itself be acting as a trigger, its environmental pressure setting the stage for these brilliant radio flashes? Or is the repeater simply an inhabitant of a common type of galaxy that, by chance, is now entering the cluster, showing us that FRBs can occur in a wide range of settings? The mystery of the progenitor remains wide open, but the Hercules Association gives us a specific place to look. It turns the cluster into a unique laboratory. By studying the gas, the magnetic fields, and the stellar populations in and around that infalling galaxy, we can search for the environmental conditions that might coax a hidden cosmic engine to scream into the radio silence, not just once, but over and over again. The brilliant, repeating radio bursts hint at a dynamic and stressful environment, one that seems to be leaving its mark on the very life cycle of galaxies. Throughout the Hercules cluster, astronomers are finding a strange overpopulation in a cosmic waiting room. We call it the Green Valley, a transitional state between two extremes. On one side, you have vibrant blue galaxies alive with the furious birth of massive, hot young stars. On the other, you have quiet, red galaxies where star formation has ceased and only the cooler, longer-lived older stars remain. The Green Valley is the in-between, a phase where a galaxy's star formation is winding down but not yet fully extinguished. Its light takes on a greenish hue in our color charts, a sign of a mixed population. In most of the universe, galaxies pass through this green valley relatively quickly, perhaps in 1 billion years or so, on their way to becoming red and dead. It's a brief stop on a one-way journey, but in Hercules something is different. The statistics reveal a clear anomaly. There are far more galaxies lingering in this green state than any standard model predicts. It's as if the cluster has a traffic jam in the cosmic commute from blue to red, with an unusual number of galaxies stuck in the transitional lane. This overabundance forces a critical question. Is Hercules an efficient killer or a master of synchronization? The first theory points to the cluster's harsh environment as a relentless quencher. As a galaxy falls into the dense cluster from the surrounding field, it experiences a series of traumatic events. Its reservoir of cold gas, the fuel for new stars, can be violently stripped away by the pressure of the hot intracluster medium, a process called ram pressure stripping. At the same time, the galaxy's own gas supply can be cut off as it enters the cluster, a state known as strangulation. These processes efficiently shut down star formation. The idea is that Hercules is so good at this quenching that it halts star production rapidly, but not instantly. Galaxies are caught in the act of shutting down, stranded in the Green Valley for longer than they would be in isolation, creating a backlog of transitioning systems. The competing theory is rooted in the cluster's unified history. Perhaps this isn't about individual galaxies being picked off one by one, but about a synchronized evolutionary pulse triggered by the colossal merger itself. The immense gravitational shock waves and the sudden influx of dense, hot gas during the merger could have delivered a simultaneous quenching shock to hundreds of galaxies at once. Imagine a forest where a sudden frost hits every tree on the same night. They would all begin to turn color in unison. In this scenario, the overabundance of Green Valley galaxies isn't a traffic jam, it's a cohort. A large population of galaxies entered the quenching phase together billions of years ago and are now, as a group, slowly fading through the Green Valley on their way to red retirement. The Green Valley galaxies of Hercules are more than a color-coded curiosity. They are a living record of the cluster's influence over the lives of its inhabitants. By studying their exact properties, how green they are, how their gas is distributed, where they sit in the cluster, astronomers can distinguish between a story of individual struggle and one of collective fate. Are we watching a slow, environmental death by 1,000 cuts, or witnessing the long-term aftermath of a single, universe-shaking event that changed the destiny of every galaxy in the city? The answer lies in the pale green light. The fate of galaxies, whether strangled or synchronized, ultimately writes its signature in the very chemistry of space. Drifting through the immense voids of Hercules is a cosmic soup, the hot intracluster gas, and it holds a hidden chemical record. Using a technique called X-ray spectroscopy, astronomers have analyzed this faint million-degree glow, breaking it down into its elemental colors. Each element, like iron, oxygen, and silicon, leaves a unique fingerprint in the X-ray spectrum, allowing scientists to measure their abundance. These so-called metals, forged in the hearts of massive stars and scattered by supernova explosions, should tell a straightforward story of galactic pollution. Over billions of years, countless supernovae within the cluster's galaxies should have enriched their surroundings, and the powerful motions of the merger should have stirred this enriched gas into a relatively even mix throughout the cluster's atmosphere. But in Hercules, the chemistry is messy. The map of metal abundance is not a smooth gradient. Instead, it's a patchwork quilt. There are pockets of gas unusually rich in iron right next to regions that are surprisingly poor. Strangely, these patches don't line up neatly with the locations of the big galaxies we see today, the presumed sources of this pollution. It's as if you sampled the air in a major city and found the concentration of car exhaust was highest over empty parks, not the congested highways. This anomalous distribution forces us to reconsider the entire life story of the cluster's gas. One compelling explanation looks to the recent violent past. The colossal merger that built Hercules was likely between 2 or 3 smaller clusters, each with its own independent history of star formation and supernova enrichment. When they collided, their distinct chemical soups were sloshed together. The patchiness we see today could simply be the incomplete mixing of these different recipes. Imagine blending 2 batches of cake batter, one vanilla and one chocolate, with only a few swift stirs. You'd end up with a marbled, uneven mixture, not a uniform brown. The turbulent, ongoing dynamics of Hercules may not have had enough time to fully homogenize the different metallicities of its progenitor clusters, yet there is a deeper, more intriguing possibility. What if the patchiness isn't about mixing, but about fundamentally different ingredients? The uneven metal map might be revealing that the pre-merger subclusters had dramatically different enrichment histories. One might have hosted a frenzied era of star formation long ago, seeding its gas with enormous amounts of iron from many type Roman II supernova. The other might have had a more delayed enrichment, with a higher proportion of its metals coming from a different type of explosion, like type Ia supernova, which produced different elemental ratios. If this is true, then the chemical patches are not just unmixed blobs. They are fossilized remnants of entire galactic communities that lived and died separately before their cosmic cities ever collided. We are looking at a chemical archaeology of the cluster's pre-merger components. This mystery cuts to the heart of how galaxies collectively shape their environment. The patchy metal map asks whether a galaxy cluster's atmosphere is a well-stirred melting pot where every galaxy contributes evenly to the mix, or a layered tapestry where the history of each neighborhood is preserved for billions of years. The answer will tell us if the most violent events in the universe erase chemical history, or if they simply shuffle the pages, leaving them still legible to those who know how to read the faint X-ray light. This chemical tapestry reveals an even more striking pattern, one etched in starlight across the sky. Cutting through the turbulent heart of the Hercules cluster is a formation of breathtaking precision, a near-perfect linear string of brilliant elliptical galaxies. Astronomers call it the string of pearls, and its existence is a geometric puzzle. In a region defined by chaotic mergers and random motions, this orderly alignment feels profoundly out of place. Each galaxy in the string is a massive, red and aging giant, and from our vantage point they appear spaced almost evenly along a straight line that stretches for millions of light years. It is as if a cosmic hand arranged them with a ruler. The immediate question is one of perspective. Are we seeing a true three-dimensional structure or a mere trick of the light? It is possible, though statistically unlikely, that these galaxies are at vastly different distances from us and only appear aligned by chance, like streetlights at different points along a highway, all lining up from a specific viewpoint. But if the alignment is real, if these giants truly form a linear chain in space, then we must ask how such fragile order survives in the cluster's violent environment. The most compelling explanation ties back to the invisible bones of the cosmos. We know the universe's large-scale structure is a web of dark matter filaments. Galaxies and clusters form at the intersections of these threads. The string of pearls could be a fossilized imprint of one such primordial filament, a cosmic backbone along which these galaxies first coalesced billions of years ago. In this scenario, the alignment is a relic of birth, a memory of the straight line along which the raw material of the universe originally flowed. The competing theory is one of destruction, not creation. Could the merger itself have forged this string? During the colossal collision of subclusters, the immense tidal forces can stretch and rearrange galaxies. It is possible that a group of galaxies was caught in a specific, narrow gravitational shear, a cosmic current that lined them up like debris caught in a streamline. This would make the pearls not a fossil but a temporary byproduct of violence, a structure that will eventually be shaken apart by future interactions. The alignment challenges our basic models of cluster dynamics. In the crowded core of Hercules, galaxies should be interacting constantly, their orbits randomized over time by close encounters. A straight line is an unstable configuration. It should not persist for long, so its very presence forces a difficult choice. Either the cluster is even younger and more dynamically active than we thought, and we are catching this rare alignment just before it dissolves, or there is a hidden, stabilizing force at work. Perhaps the dark matter halos of these galaxies are aligned along the same filament, creating a subtle gravitational channel that helps maintain the structure against the chaos. The string of pearls is more than a celestial curiosity. It is a direct test of our understanding of motion and memory in a galaxy cluster. Are we looking at the enduring skeleton of the cluster's birth or the fleeting scar of its most traumatic growth spurt? The answer lies in the silent, geometric perfection of these aging giants, holding their line against the tide of chaos. That geometric perfection of aging giants gives way to a far more subtle signature, one written in a color of light our eyes can never see. Peering into the spaces between those galaxies, the Spitzer Space Telescope captured a faint, enigmatic glow in the infrared. It wasn't the smooth, predictable heat of ordinary dust or the sharp lines of familiar molecules. Instead, the data revealed broad, unidentified emission bands, blurred, hump-shaped features in the spectrum of the intracluster medium. These are not the fingerprints of any known cosmic substance. They are spectral ghosts, and their presence in the brutal environment of a galaxy cluster is a profound surprise. To understand why, we need to consider the carriers, the materials that could possibly produce such a signal. The leading suspects are complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. Picture them as tiny, flat flakes, like microscopic pieces of soot or the skeletal frameworks of graphite. On Earth, they're found in everything from charcoal to car exhaust. In the calm nurseries of our own galaxy, PAHs are common, thriving in the sheltered cocoons around young stars where they absorb ultraviolet light and re-emit it in these very infrared bands. They are, in a sense, the basic building blocks of carbon-based chemistry scattered throughout the cosmos. but the intracluster medium of Hercules is no stellar nursery. It is a hellscape. The space between galaxies is flooded with intense X-rays and ultraviolet radiation from countless sources, and roiled by shock waves from the ongoing merger. This harsh radiation field should be a destroyer, shredding fragile complex molecules like pHs in short order. It's like expecting a delicate paper sculpture to survive intact in the heart of a blast furnace. The mere presence of these emission bands suggests something is shielding these compounds, or that they are being continuously produced in vast quantities to replace what is destroyed. This leads to the deeper mystery. What process could possibly be at work? One radical idea is that the violence itself is the factory. The merger-driven shock waves that compress and heat the gas might also be triggering unexpected chemistry. Could the collisions between dust grains or the fragmentation of larger carbonaceous particles in these shocks be manufacturing these complex organics on the fly? It would be a case of cosmic destruction giving birth to chemical complexity. Alternatively, the molecules might not be free floating at all. They could be locked safely inside dense, hardy dust grains, like precious gems encased in armored vaults protected from the external radiation and only revealing their infrared signature when occasionally exposed. The implications stretch far beyond Hercules. If complex organic molecules can form and persist in such an extreme place, it reshapes our understanding of where the ingredients for life might be found. It suggests that the seeds of carbon chemistry, the very precursors to the stuff we are made of, are not confined to the safe, quiet corners of galaxies. They might be forged in the universe's most violent workshops and scattered into the great voids between galaxies, perhaps even raining down onto future planetary systems. The unidentified infrared bands are more than a spectroscopic puzzle. They are a faint, warm hint that the universe's capacity for complexity might be far more robust and far more widespread than we ever dared to imagine. These complex molecules drift through a brutal environment, one that is actively reshaping the smallest and most vulnerable inhabitants. Among the hundreds of galaxies within the Hercules Cluster, a quiet but relentless metamorphosis is underway. Many of its dwarf galaxies are caught in a dramatic transition, visibly changing form before our telescopes. These small, often misshapen collections of stars and gas are being transformed from gas-rich, irregular blobs into smooth, gas-poor spheroidals at a pace that defies expectation. It is a cosmic makeover driven by violence, and Hercules appears to be a uniquely efficient salon. To understand this, we must follow the journey of a dwarf galaxy as it ventures into the cluster. Initially, such a galaxy might be a loose, messy assemblage, rich with the cold hydrogen gas needed to birth new stars, but the cluster environment is unforgiving. Two primary forces work in concert to strip away its identity. The first is known as harassment. This is not a single violent event, but a death by 1,000 gravitational cuts. As the dwarf galaxy orbits through the crowded cluster core, it experiences countless high-speed encounters with other galaxies, and more importantly, with the cluster's own immense gravitational field. Each passage tugs and pulls, distorting the dwarf's shape, shaking loose its stars and gas, and gradually heating up its stellar population so they move on more random, chaotic orbits. Think of it like a small, fragile boat sailing through a stormy sea filled with other vessels. Every wave and near collision damages its structure, slowly breaking it apart. The second force is far more direct, ram pressure stripping. Here, the intracluster medium itself becomes the agent of change. That thin, superhot gas that fills the space between galaxies might seem insignificant, but when a dwarf galaxy moves through it at speeds of hundreds of kilometers per second, it feels like a hurricane-force wind. This wind exerts immense pressure, and it acts directly on the dwarf's own cold gas reservoir. The galaxy's stars, bound tightly by gravity, are mostly unaffected. But the diffuse gas clouds between those stars are not so lucky. They are literally swept away like dust from a table by a strong gust. The galaxy loses its star-forming fuel in one brutal, continuous event. We can see this process in action with specific dwarfs in Hercules. Galaxies like insert example name if available, otherwise a general description. A faint smudge designated Hercules W1 show clear tails of gas being stripped from their bodies, trailing behind them like cosmic comet tails. Others appear already deflated, their irregular shapes smoothed into faint, roundish balls of old stars, all signs of their gas-rich youth erased. The unexplained aspect is not that this happens, but how swiftly and completely it occurs. The transformation seems accelerated in Hercules. Dwarfs are progressing from lively, gas-filled systems to quiescent, red spheroidals faster than models predict. This suggests the environmental effects here are exceptionally potent. Why? The leading suspect is the cluster's turbulent merger history. That colossal collision did not just leave behind radio halos and disturbed gas, it created a legacy of chaos. The intracluster medium is likely more turbulent with stronger and more tangled magnetic fields. The gravitational potential is more uneven, making harassment more effective. It is as if the cluster's atmosphere is still agitated from the ancient impact, creating a more abrasive environment for anything moving through it. The dwarf galaxies are not just sailing through a hot sea, they are sailing through a hot sea filled with unpredictable currents and whirlpools. This added turbulence may enhance ram pressure, allowing it to reach deeper into a dwarf's core, or it may make harassment more frequent and severe. The rapid transformation of these smallest galaxies is a subtle but critical clue. It tells us that the violence of a cluster's birth does not end with the merger of the giants. It echoes for billions of years, shaping and sculpting the tiniest members of the cosmic city with a startling, and still not fully understood, efficiency. The brutal efficiency stripping dwarf galaxies of their gas might be fueling an even more energetic process. Gamma-ray telescopes have detected a faint but persistent glow emanating from the Hercules cluster's core, a signal of the most powerful particles in existence. This is a cosmic ray excess, a whisper that somewhere in that turbulent heart, nature's particle accelerators are running at full blast. Cosmic rays are not rays of light, but atomic nuclei, mostly protons hurtling through space at nearly the speed of light. They are the universe's ultimate bullets, and when they collide with other matter or light, they can produce gamma rays, the highest energy form of light. The fact that Hercules is a source of these gamma rays means it is actively producing, or at least confining, these ultra-relativistic particles. The mystery lies in identifying the exact machine that's doing the accelerating. One prime suspect is the merger shock itself. Those colossal waves of energy, still rippling through the cluster's gas from the ancient collision, could be acting like continent-sized particle accelerators. As electrons and protons get caught in these shock fronts, they can be boosted to incredible energies, a process known as diffusive shock acceleration. It's a natural, if extreme, explanation. Yet, the observed gamma-ray signal has a specific energy signature that doesn't perfectly match what we'd expect from shocks alone. This mismatch opens the door to more exotic possibilities. Another compelling source is the central supermassive black hole in NGC 6166. Its powerful jets and accretion disk create a maelstrom of magnetic fields, ideal for flinging particles to near-light speeds. The flickering, knotted jets of Hercules could be direct evidence of this chaotic acceleration process in action, potentially flooding the core region with high-energy cosmic rays. Then there is the most speculative and potentially revolutionary candidate, dark matter annihilation. If dark matter is made of theoretical particles like WIMP, weakly interacting massive particles, they could occasionally collide and annihilate each other in the dense dark matter halo of the cluster. Such an event would release a burst of energy, including gamma rays. The core of Hercules, with its overmassive black hole and complex dark matter distribution, would be one of the most likely places in the universe for such a signal to appear. Pinpointing the true origin is maddeningly difficult because of a fundamental property of galaxy clusters. They are cosmic calorimeters. Their immense gravitational fields and tangled magnetic fields act as a nearly perfect trap. Once a high-energy cosmic ray is produced inside a cluster, it struggles to escape. It spirals around magnetic field lines, bouncing back and forth, its energy slowly dissipating over millions of years. This means the gamma-ray glow we see isn't necessarily a pinpoint to a single factory. It could be the accumulated, diffuse glow from particles produced by many different events over a vast span of time. The excess we detect is the combined echo of eons of violence. Hercules, therefore, isn't just a source of cosmic rays. It's a vast containment vessel for the universe's most energetic particles. It challenges us to separate a single note from a cosmic choir that has been singing for billions of years. Are we seeing the steady hum from an ancient shock wave, the intermittent roar from a black hole's jet, or the faint, telltale crackle of dark matter itself unraveling in the darkness? This faint gamma-ray glow is a lingering echo of ancient violence, but just how ancient? The precise timing of the colossal merger that built Hercules is one of the most contentious puzzles in its entire story. We see the wreckage, we map the debris streams, but the exact moment of the cosmic crash remains stubbornly elusive. Different scientific methods, each examining a distinct piece of evidence, point to different chapters in the cluster's past. It is as if three detectives arrived at the same chaotic crime scene, and one declared the event happened yesterday, another a week ago, and a third a full month in the past. The first detective examines the hot gas. By studying the dynamics and temperature of the intracluster medium, astronomers can model how long it would take for the violent shock waves from a merger to dissipate and for the gas to settle, or in Hercules' case, to remain disturbingly unsettled. This method, focusing on gas dynamics, suggests a relatively recent impact. The calculations point to the main collision having occurred perhaps only 1 to 2 billion years ago. The gas is still churning, its temperature map still showing the sharp edges of recent shock fronts. It hasn't had time to relax into a smooth, cool core, which aligns with the idea of a cosmically recent trauma. The second detective watches the stars by meticulously tracking the motions of hundreds of galaxies within the cluster. A field known as galaxy kinematics. Scientists can run complex simulations to rewind the cosmic clock. They input the current velocities and positions of these galaxies and let gravity play the tape backward to see when they were most likely concentrated in separate, colliding groups. This kinematic approach often yields an older date. These models frequently point to the merger's peak occurring around 2 to 3 billion years ago. The reasoning is that it takes a long time for the violent, streaming motions from the collision to randomize into the more chaotic orbits we expect in a mature cluster. The fact we still see such coherent streams of galaxy motion suggests the event was farther in the past, giving those streams time to stretch out but not yet fully dissolve. Why such a glaring discrepancy? The answer lies in the different clocks each method is reading. The hot gas reacts almost instantly to a merger. It is shocked, heated, and sloshed around immediately. But it also cools and settles relatively quickly on timescales of 1 billion years or so. Its state tells us about the most recent major disturbance. The galaxies, however, are like massive, slow-moving buoys in a gravitational sea. Their motions are set by the merger's initial kick, but they are so ponderous that they preserve that kinematic signature for much longer. They are telling us not necessarily when the last shock hit, but when the fundamental gravitational dance was set in motion. They could be remembering an earlier, more defining stage of the collision, while the gas is recording the final, messy coalescence. This timeline is not an academic footnote. It is the master key to understanding the lifespan of nearly every phenomenon we've explored. take the colossal radio halo, that fading echo of synchrotron radiation. The relativistic electrons that produce that radio glow lose energy continuously. If the merger happened 3 billion years ago, that radio relic should be vastly fainter than what we observe, unless some hidden process is continuously re-accelerating particles. A more recent merger, say 1 billion years ago, makes the bright radio halo far easier to explain. It's simply a younger, fresher echo. Similarly, the overabundance of green valley galaxies, the disturbed core, even the survival of delicate structures like the string of pearls all hinge on this chronology. Was the violence so recent that we are seeing a cluster in the throes of a brief, tumultuous adolescence? Or are we observing a system that has been settling into a chaotic middle age for eons? The conflicting dates force us to consider a radical possibility. Perhaps we are not looking at a single, clean collision, but a drawn-out, multi-stage event, a series of cosmic crashes that unfolded over billions of years, leaving each method to timestamp a different chapter of the same epic war. This conflict in the timeline leaves a lasting mark on the galaxies themselves, a thermal scar written in the motions of their stars. The galactic halos within Hercules are running a fever. When astronomers measure the velocity dispersion of stars in the extended halos of certain cluster galaxies, they find a puzzling excess of heat. In simpler terms, the stars in these vast, outer regions are whizzing around at much higher speeds than they should be. For an isolated galaxy of the same mass and type, you'd expect a certain calm, a predictable range of stellar speeds dictated by the galaxy's own gravity. But here, the stellar motions are frantic, as if the galaxy has been shaken to its core. This too-hot condition is a direct signature of violence, a record of the tidal forces that have pummeled these galaxies over billions of years. To measure this, scientists use a technique called spectroscopy. They don't track individual stars. Instead, they take the combined light from a galaxy's faint outer halo and spread it into a rainbow. Within that spectrum, the absorption lines, the dark fingerprints of specific elements, are not sharp. They are broadened and blurred. This blurring is the key. It's caused by the Doppler effect. Some stars are moving rapidly toward us, others rapidly away, and their combined light smears the line. The greater the spread in velocities, the broader the line becomes. This spread is the velocity dispersion, and in Hercules, for many galaxies, that number is strikingly high. It tells us the gravitational environment these stars feel is more intense, more chaotic than what the visible mass of their home galaxy can provide. Something has pumped extra energy into the system, heating it up. The prime suspect is tidal heating. Imagine a galaxy not as a solid object, but as a loose swarm of bees held together by gravity. Now imagine that swarm flying perilously close to another, much larger swarm. The gravitational pull from the larger group doesn't just tug on the small swarm as a whole, it stretches it. The bees on the side closer to the giant swarm feel a stronger pull than those on the far side. This differential force, the tide, stretches the small swarm, distorting its shape and critically transferring energy to the individual bees. Their orbits become more energetic, more random. They move faster. This is what happens to a galaxy's halo when it undergoes a close encounter with another massive galaxy, or, more catastrophically, when it is yanked and pulled by the immense, uneven gravitational field of the entire cluster during a merger. The stars in the outer halo, which are only loosely bound, are the most vulnerable. They get a gravitational kick, their orbits are scrambled, and the halo's temperature rises. This leads to a crucial insight about how galaxies are prepared for life in the big city. Many of these overheated galaxies likely did not experience this heating for the first time within Hercules itself. They were pre-processed. Before falling into the colossal cluster, they were members of smaller galaxy groups. In these suburban environments, galaxies are closer together and move more slowly relative to each other. This makes close encounters and even mergers far more common and effective. A galaxy can have its halo tidally heated or even partially stripped during a slow-motion dance with a neighbor in its home group. By the time that entire group, now a bound unit, finally plunges into the violent core of Hercules, the galaxies within it are already stressed, already heated. They are not pristine newcomers, they are seasoned survivors, bearing the scars of their local history before facing the cluster-wide onslaught. This pre-processing is a fundamental part of the hierarchical build-up of cosmic structure. The universe doesn't build clusters from raw, individual galaxies. It builds them from groups, from small-scale structures that have already been assembling and interacting for eons. Hercules, in its present state, is a snapshot of this final assembly phase. The feverish halos of its galaxies are a living archive of that two-stage history. First, the intimate gravitational encounters in the quiet suburbs of a group, and then the brutal, cluster-wide turbulence of the metropolitan core. By taking the temperature of these halos, we are reading a biography of gravitational encounters, a story that begins long before a galaxy ever enters the dazzling, violent heart of the cluster. This feverish history of gravitational encounters has left the cluster's heart in a state of profound contradiction. After all we have witnessed, the violent mergers, the overheated halos, the colossal shock waves, you would expect the very center of Hercules to be a raging inferno of activity. In other merging clusters across the universe, the central galaxies often host brilliant, screaming beacons known as active galactic nuclei. These are supermassive black holes in the midst of a ferocious feast, their accretion disks glowing so brightly they can outshine every star in their host galaxy combined. They are the expected consequence of chaos, as mergers funnel vast rivers of gas directly into the black hole's maw. Yet, when we look at the core of Hercules, at the titanic galaxy NGC 6166 with its 10 billion solar mass black hole, we find something deeply unexpected: silence. The core is quiet, the monstrous engine is idling. This is the paradox of the quiet core. Here we have a cluster forged in a cataclysm, a place where galaxies are still streaming from the impact, where the gas is shock-heated and turbulent, and where an overmassive black hole sits at the gravitational epicenter of it all. By every right, this should be the site of the most spectacular active galactic nucleus in the local universe. But the data tells a different story. Observations across the electromagnetic spectrum, from radio waves to X-rays, show that the black hole in NGC 6166 is currently in a low luminosity state. It is not pouring out immense amounts of radiation. Its jets, while powerful, are not in a frenzied outburst. Compared to the brilliant quasars seen in other merging systems, this giant is napping. So what happened to the feast? Why is the most violent place we know also one of the quietest at its very heart? Astronomers are probing three compelling possibilities, each a different take on cosmic supply and demand. The first is simple: the black hole could be in a temporary dormant phase. Even the mightiest engines need fuel, and the merger, for all its violence, may have disrupted the supply lines. Think of it like trying to drink from a fire hose that is being whipped around in a storm. The chaotic motions stirred up by the collision could have prevented the gas from settling into a stable, dense disk around the black hole. Instead of a smooth, continuous inflow, the fuel might be arriving in erratic clumps and bursts, leading to periods of activity followed by long stretches of quiet. We might simply be observing Hercules during a cosmic intermission, a brief pause before the next act of furious accretion begins. The second idea is far more elegant and points to a state of perfect, self-regulating balance. This is the concept of feedback in its most refined form. Recall the cooling flow problem, where the black hole's energy is thought to reheat the surrounding gas, preventing runaway cooling and star formation. In Hercules, this feedback loop may have reached a state of equilibrium so precise that it appears as quietude. the black hole could be consuming just enough gas to produce the gentle, continuous outflow needed to keep the core gas hot and turbulent, but not so much that it erupts into a brilliant, unstable quasar. It is a masterful act of cosmic governance, a black hole acting not as a voracious monster, but as a subtle thermostat, maintaining the cluster's atmosphere with the faintest whisper of energy. In this scenario, the quiet core is not a sign of inactivity, but of supreme control. The third possibility turns our view of the merger dynamics upside down. Perhaps the violence of the collision itself is the very thing suppressing the black hole's activity. When two clusters merge, the central black holes of their dominant galaxies are thought to eventually spiral together and coalesce. During this long, slow dance, complex gravitational interactions can slingshot stars and gas away from the very center, effectively starving the black hole at the most critical moment. Furthermore, the immense turbulence in the core gas might prevent it from cooling and condensing onto the black hole in the first place. It is a cruel irony. The event that should deliver the ultimate banquet might also be the one that keeps the table just out of reach. This profound quiet at the center of the storm forces us to reconsider the life cycle of cosmic giants. Is the brilliant quasar phase a fleeting, teenage outburst in the life of a supermassive black hole, with the long, quiet adulthood of maintenance and balance being the true norm? Or is Hercules showing us a unique path where the specific choreography of its merger left its central engine in a state of suspended animation? The silence of NGC 6166 is not an absence of evidence, it is evidence of a deeper, more subtle physics at work. In a universe that often shouts its mysteries, sometimes the most profound questions are asked in a whisper. From phantom gases and ghostly lights to impossible structures and cosmic collisions, the Hercules Cluster is a treasure trove of cosmic conundrums. It stands as a testament to a universe that is far stranger, far more dynamic, and far less settled than we ever imagined. Every anomaly we've walked through, from the flickering jets of Hercules to the silent core of its most massive galaxy, is not an isolated oddity. They are interconnected symptoms of a deeper, more complex reality. The missing hot gas, the overpopulated green valley, the overheated galactic halos, each one is a piece of a single, sprawling puzzle. They force us to confront the limits of our models, to admit that our understanding of dark matter, galaxy evolution, and even the life cycles of black holes is still a work in progress. This cluster is not just an object in the sky. It is a cosmic laboratory, a natural experiment conducted on a scale we could never replicate, showing us where our theories succeed and, more importantly, where they spectacularly fail. Which of these 25 puzzles fascinates you the most? Is it the haunting presence of the ultra-diffuse galaxies, those cosmic ghosts that should not exist? Or is it the sheer, mind-bending scale of the Hercules corona Borealis Great Wall? A structure so vast it seems to defy the universe's own rules? Let us know in the comments below. The conversation about these mysteries is just beginning, and every new observation, every new telescope brings us closer to rewriting the textbooks. If you found this journey through cosmic contradictions compelling, don't forget to subscribe for more deep dives into the universe's greatest enigmas. There are always more mysteries waiting just beyond the edge of our understanding. Until next time, keep looking up.